The PDB Reader is a required module whenever your builder workflow involves a protein structure. It provides the essential first step for preparing a protein or protein ligand complex prior to system construction. In this demo, we introduce the advanced options of the PDB Reader. Since there are 14 options in total, which can be difficult to explain all at once, we will instead present examples to illustrate each option in detail. We have already demonstrated the basic usage of the PDB Reader in a previous session. Here we will begin from step 3 to highlight the advanced options. If you need instructions on the basic functions, please refer to the earlier demo first. We're diving into the fascinating world of structural biology using a PDB Reader module to build a specific ADC, trastuzumab deruxtecan. Part 1. Understanding trastuzumab deruxtecan. Before we dive into building the ADC in PDB Reader, let me give you a brief introduction to trastuzumab deruxtecan. Trastuzumab deruxtecan is an important antibody-drug conjugate, or ADC, that received FDA approval in 2019. It has been used in the treatment of several cancers, including gastric, breast, and colorectal cancer. This ADC is based on a humanized IgG, 1-kappa antibody that targets the HER2 protein. The key components of this conjugate are as follows. The antibody is trastuzumab. The linker is MCGLY-GLY-FEGLY, which is cleavable, and the payload is a DX8951 derivative, also known as DXD, which inhibits DNA topoisomerase 1. The conjugation takes place randomly via reduced interchain cysteines. In our build, the drug-to-antibody ratio, or DAR, is set to 8, which means we'll be using all 8 cysteines in the system. Part 2. The PDB Reader procedure. 1. Chain selection. The PDB file includes several protein chains, along with water molecules. In this demo, we will load multiple protein components together without water chains. 2. Disulfide bond. Before we begin, we need to remove the disulfide bonds. The reason for this step is that our conjugation will occur through reduced interchain cysteines. Since we want to build a DAR of 8, we have to eliminate the pre-existing disulfide bonds, so go to the disulfide bond section and delete all of the listed bonds. 3. Covalent bond. Creating a new covalent ligand begins with naming it. The system combines the residue character with your chosen short name. For example, attaching the default name LIG to a cysteine results in CLIG. You can add your ligand by drawing it in the sketchpad. To simplify residue selection, enable the Display Surface Protein Only option. Once the ligand is drawn, define the covalent bond during the Validate Structure step. This ensures the 2D structure is fully connected, hidden hydrogens are handled correctly, and the intended covalent bond is properly assigned. Next, choose a force field such as OpenFF, which is recommended for larger ligands to prevent slowdowns. After validation, click Submit, then Add to finalize the process. The new covalent ligand will be incorporated into the system with the specified covalent bond. Now let's move on to conjugated covalent ligands, which is the module we'll actually be using for our ADC. Here we need to set up both the payload and the linker. Click the magnifying glass to search for the DX-8951 derivative, or DXD, payload, and then repeat the process for the MCGLY-GLY-PHEGLY linker. Because our target DAR is 8, we'll be using every cysteine in the system. To do this, search for CYS in the Residue drop-down menu, click Add Residue, and select all 8 cysteines. Next, click Check Structure. You'll see the initial model displayed, with the protein on the lower left, the linker on the lower right, and the payload in the upper section. The next step is to connect these three parts by adding the necessary atoms and bonds to form the complete conjugated structure. Once everything is connected, click Apply to finalize the model. Ensure that the structure is fully connected and that no implicit hydrogens remain. Finally, click Add to bring the ADC into the system. At this point, you should see all 8 trastuzumab deruxtecan conjugates added successfully. 4. Terminal cappings. In this option, terminal capping is applied by default. In this case, you may choose neutral caps, charged caps, or apply custom caps depending on your modeling needs or the force field requirements. Here, we will keep the default selection. The building process may take a while, as the module generates the force field and adjusts the protein residues to properly position the conjugates on the protein surface. Part 3. Result. You've successfully built a complex antibody-drug conjugate using the PDB Reader module. This is a powerful tool for working with various molecular structures. If you found this tutorial helpful, be sure to check out other tutorials in the playlist and the links to our website in the description.